Hello, and welcome to the second episode of what has become a series about optimizing with constraints. Have you ever been to an elementary school fundraiser or a carnival night? Or maybe have you been to the attendance office during GOFA? Sometimes they have what's called a bucket raffle or a basket raffle. They usually have around 20 prizes. They're donated by parents or community members. A lot of times their gift baskets is what the prize is. So you'll have like a travel basket with road games, a movie night basket with movies and popcorn, a coffee basket. The options are endless. Just ask your aunts about it. It's a big thing. So you buy tickets, usually for $1 or $2 each, and you put your tickets in the buckets for the prizes that you want to win. And then at the end of the raffle, they draw a winning ticket for each prize. Have you ever wondered how to mathematically maximize your total profits? I have, and it works. So let's take a look at how I calculated the optimal amount of tickets to invest into this basket. Let's consider the case where you just have one big raffle, one bucket, one prize, simple. You want to know what number of tickets to buy to maximize your total raffle profit. What does profit mean in this case? Raffle profit is composed of two parts, probability and payout. Probability just means how likely you are to win the raffle. So if you manage to get an estimate of how many tickets are already in the bucket, we'll call that T, the number of tickets. The probability that your ticket is drawn, if you put in X tickets, is just X over the total number of tickets, X plus T. So probability is X over X plus T. Payout is how much you make if you win. So if you can estimate the value of the prize, we'll call this V. This is sometimes hard to do, especially if it's a basket. But from the value, we need to subtract how much we spent on tickets. This is the cost per ticket, S, times the number of tickets we bought, X. So now we have our probability and our payout. How do we combine them together? Well, if we say that the probability is 0.5 and the payout is $100, then we can say that we'll get $100 approximately half the time. So this averages out to $50 of total profit every time. What we did there is just simple multiplication, 0.5 times 100. So this is how we get the final formula for profit, probability times payout. Let's take a look at how this looks on a graph. Let's say there's 20 tickets in the bucket, tickets cost $2, and the prize is worth about $100. The x-axis here is how many tickets we purchased and put in the raffle, and the y-axis is how much profit we can expect to make from it. So when you buy 0 tickets, obviously you can't expect to make any profit because then you don't have any chance of winning. And when you buy more than 50 tickets, your chances of winning are really good, but you're guaranteed to lose money, which is why it's negative, because you're already paying for more in tickets than the value of the prize. The graph itself, as you can see, it looks like a bit like a parabola, but it's bent to the left. So we want the sweet spot right to the left of the center. This says that if we buy 17 tickets, we can expect to make a profit of just over $30. So how can we mathematically find this point? Since this isn't exactly a parabola, we can't use any formula that we learned in algebra. So let's recall how we optimize a function using calculus. Right at this point that we want, 1730-ish, the tangent line has a slope of 0. So let's derive our function and set it to 0. By multiplying probability and payout, we get this nice rational function, so we can just use the quotient rule. Remember that the variables v, s, and t don't change, so we treat them like constants and not variables when we derive. So when we derive the top, we get v minus 2 times s times x, and when we derive the bottom, we just get 1. Let's multiply all this out and cancel, and we're left with just vt minus 2sxt minus sx squared, all over the sum of t and x squared. I'm going over all the nitty-gritty math quickly, so if any of it doesn't make sense, I'd recommend stopping and trying to figure it out yourself. So now we just need to set this to 0. We can multiply both sides by the denominator, make it go away. We just need to keep in mind that 0 won't be in the domain of our final answer. Just because it cancels out doesn't mean it's still not there. So just unlike before, which wasn't a parabola, we actually do have something in the quadratic form. So let's just use a quadratic equation, and we get finally that x equals 2st plus or minus the square root of 4s squared ts squared plus 4tvs all over negative 2s. And in this case, if you look at the graphs, it actually turns out that the relevant answer is always going to be the one when you do subtraction instead of addition, which is why I only have the minus sign here. So So this is the formula for the optimal number of tickets to buy for any raffle. It works for bucket raffles, normal raffles, even the lottery if you have a few $1,000,000 laying around. But this is boring. Let's step back and look at the bucket raffle as a whole. If you wanted to maximize your profit totally, you would just repeat the same formula for each bucket. But what if, like me, your mom bought you a certain number of tickets for a bucket raffle every year and then just set you loose? How do you decide which buckets you're going to put the tickets in? Contrary to what you might think, the answer is not just scaling the entire set of optimal ticket values down until you reach 50. We'll see proof of that at the end. We have to start the optimization process already with the constraint in mind and optimize from there. So how do we define this more formally? First of all, let's redefine our constants. Instead of t and v being numbers, let's make them vectors or lists of numbers. So the first element of v is going to be the value of the first prize. The first element of t will be the number of tickets in the first basket, and so on and so forth. S is still just a number, the price of one single ticket, because that never changes throughout the bucket raffle. With that in mind, let's more formally define our functions too. We're going to call profit f, and we're going to say that it takes a vector x instead of just a number x. And x is the vector of all the numbers of tickets that you're going to invest in each basket. So just like in the last episode, we're also going to make our constraint a function, and in this case, it's the exact same function as the last episode. So we're going to say that g of x is the sum of x, which must equal c, and we're going to call c 50. That means that we only have 50 tickets. All the numbers of our tickets add up to 50 because we only have 50 tickets. So how do we find the best vector x that gets us the highest value of f while still keeping g true? Well, let's try what worked last time using Lagrange multipliers. And let's do it a little more formally this time, the actual way that you're going to learn in calculus. Instead of using the normal derivatives, let's use the partial derivatives. This basically just means that we derive with respect to one variable of the entire vector x, and we pretend that all the other variables are constants. So kind of like what we did when we say v, t, and s are constants, we're going to do that with all the other values of x. When we want all the partial derivatives in one vector, we call it the gradient of the function. So let's find the gradient of f first. Remember that f is actually the sum of all the profits, but each value of the x factor can only impact its own term. So each partial derivative of f is actually just the same derivative equation that we already calculated. So we just need to specify that for each partial derivative, we're actually looking for the ith element of t, v, and x. So that ended up being really easy. So let's take a look at the gradient of g. Remember that g is x1 plus x2 plus x3, etc. for each value of xi. Let's remember that the partial derivative that we just pretend all the rest of the x's are constants. So for the partial derivative with respect to x1 is just going to be 1 because the partial derivative of x is 1. And then the rest of the x's are just going to be a whole bunch of zeros because we're treating them as constants now. So this means that the gradient of x is just, the gradient of g of x, is actually just a vector full of 1s. So this time, to scrounge up our 11 equations and 11 unknowns, we need to set the two gradients collinear with each other, meaning that you can scale one of them to get the other, and lambda is the scalar. And then finally, the constraint function is the last equation. In this case, that means that all of the partial derivatives of f will equal lambda, because all of the partial derivatives of g are 1, and the sum of x is going to equal 50. That's just our constraint equation. The only problem here is that there's not really a simple, clever way to get this system of equations solved, like there was last time. Even when I plugged it into Z3, which is a super powerful theorem prover, it ran forever. So in practice, you don't want to have to look for a clever solution every time you go to a bucket raffle. So let's look for a more algorithmic solution. So let's take a step back and look at what we already have. We have formulas for all the partial derivatives of f, meaning the gradient. What really is the gradient, though? A gradient is really just a vector full of slopes in different directions. So let's simplify it. Let's just look at the 2D. The slope at a certain point is always going to point towards the steepest direction up. And when we go to the left, it's going to be negative. When we go to the right, it's positive. When we go to the left and down a bit, it's going to get to a lower value, and to the right a bit, it's going to be a lower value but positive. So actually, if we just take a point and we subtract by the slope, it's going to bring us closer and closer to the bottom of the trough here. But back to the multidimensional case, one really helpful property of the gradient is that it actually points to the steepest direction in every single direction, not just the one direction that we have for the slope. It's a little out of the scope of this video to explain exactly why, but it's super helpful and really fascinating actually. So let's take a look at a generic 3D graph. In this case, x and y are both independent, like we saw in the last video, and the height, or z, is the output variable. So we want to find the lowest point on the surface. We can pick a starting point, and using that point, we can find the gradient. Remember that the gradient points in the direction of steepest ascent, the positive direction. So if we just go backwards from that, taking small steps and recalculating the gradient, we can roll right down the hill to find the bottom. The only problem here is that there's no constraint. There's no way to make sure that we stay exactly where x plus y is equal to 5, for example. Okay, consider this. You're balancing a marble on a sheet of paper. How do you make sure that it stays on the hamburger-style center line? The answer is pretty simple. Now imagine the line of the constraint, x plus y equals 5. If we rearrange the equation a little, we can set the entire constraint function to 0. So this becomes a measure. This is not like a unit accurate measure or anything, but it's still a measure of how far away any point is from the constraint line. So if we square it, we get a trough that forces any point to roll down into the trough of the constraint. And this actually works with any constraint curve we want. So say we want to keep all the points on a circle with radius 2. So first, the constraint function is that x squared plus y squared equals the radius squared. So x squared plus y squared minus 4 equals 0. If we just square this, this trough keeps all the points rolling into the circle. So back to our gradient descent function. We still want to maximize the function, but we need the point to still stay on the constraint line. So we can overlay our constraint trough, so to speak, by adding it onto the original function. So this warps the entire surface. It's like bending that paper with the marble, or nerd thing. It's warping the entire surface so that it still has the same features as the original. It's just folded with the constraint trough. So let's put this into practice. First of all, what we just saw was gradient descent, where we tried to minimize a variable. I only explained it like this because it makes so much more intuitive sense to think about a point rolling down a surface or into a trough or something like that. In this specific problem though, we're actually trying to maximize our profit. So everything I just showed you was actually backwards. We're going to make the point roll up surfaces and come out of troughs. So what's the function we're trying to maximize? Let's call it the reward. This is because normally people call it the cost function when they're trying to minimize it, so let's just call it the opposite, the reward function. And the reward function takes just the vector x. It's made of, first of all, the profit function, obviously, because that's what we're trying to maximize. And then we're going to subtract g of x squared. And we're subtracting because of adding, because again, everything is backwards when we're doing gradient ascent. So the last part we need for gradient ascent is, of course, the gradient. So given a certain xi, what's the partial derivative of the reward function, that is? We already know the partial derivative of f. This is easy. For g, let's just bring the 2 back, and because of the chain rule, multiply by the partial derivative of g. Since the partial derivative of g is just 1, as we found, we can get rid of that entirely. So this is the final answer that we need. This is the reward function that we're trying to maximize, and we have its gradient. And that means we have everything we need to ascend. This video isn't meant to cover the computer science behind this. If you're really curious though, the code is on my GitHub and there's a link in the description. Basically what this is doing though, it's just recording the reward function to see how well we're doing, and then adding the gradient to x and recalculating the gradient. Once it's all done doing gradient ascent, I have it graph the reward function. As you can see, it pretty quickly finds a good solution. This isn't guaranteed to be the best solution, but I started it from a whole bunch of different points, and it always converged at this same point here, so there's a pretty good chance that this is the best point that we want. I also promised that there would be proof that it's worth doing this, that it finds a better solution than just optimizing each individually and scaling it down to 50 tickets. The truth is, I actually have no idea why this is better, but we prove here that it is. When you start at the optimized point and do gradient ascent from there, it's able to find an even better solution. So the reward function does go up about 2 points. The first optimized solution that we got and then the gradient ascent solution, they're pretty close. And the first solution is a good approximation, but if you want the best chance of destroying these elementary schoolers' dreams, it's better to eke out these last 2 reward function points with gradient ascent. Okay though, let's address the elephant in the room, and there's actually 2 of them. The first elephant is that there's not 50 tickets, there's 50.4 tickets. So using this method, you aren't guaranteed to exactly fulfill the constraints. The gradient ascent algorithm got to the top, but it realized that it could stand just a little bit taller if it moved off the trough a tiny bit. You could change the reward function to reward the algorithm more for staying in the trough, but personally, I like that the algorithm is free to have a little creative expression. It means that it's less likely to fall into a local maximum or something like that. The second elephant in the room, though, is that you can't have 9.087 tickets. All of these are non-discrete values of tickets. This is where the trough method actually comes in really handy. You can change the reward function to reward the algorithm for settling on whole numbers. You just need to use a little modulo arithmetic. I'd encourage you, if you're really interested about this, try to figure out how to do this and modify the code to get it working. So given these prize values and the number of tickets in their buckets, this is the optimal ticket placement. I'm sure you're aware that the title of this video is a joke, but I should say it again anyway. Some kid is spending their entire allowance because they want a new scooter, and yeah, it's mean of you to just rig the whole thing. This is, purely for the math behind it. Don't take it personally or anything, elementary schoolers. Once again, this video is also made with manim. Once again, I encourage you to check it out. It's super cool. This video is also recorded on a U of M microphone, so I'd also encourage going to college. Go to college because they let you use their stuff. Like this microphone. Thank you for watching.